Good evening. This is the continuation of the presentation on less is more reasoning uh, paper. Um, and I guess what we were headed was on the
I think you're down to results, right?
yeah, we were there. Okay. Um, so in order to um, I guess compare how the TRM uh, related to or how its output compares to the HRM um, architecture. Um, the authors used the same data sets, Sudoku, Maze Hard, and Arc, AGI 1 and 2, um, and then they show the results in tables 4 and 5. Come on, mouse. Um, so yeah, so I don't have the results from the other one. So they talk about what the different data sets were and um, I guess how they're structured and what they solve, um, or what problem they present to the models. And no, um, they I don't see the comparison with the HRM. So we saw the earlier at the start of the paper, they talked about how the results were better, but it may be that their um, their models being so tiny and the few layers that it has that it may be overfitting the results so that they're just uh, gonna work are better just for these type of problems instead of generalizing it. Um, they claim that the use of uh, data augmentation improves the effectiveness for generalization um, by repeatedly going over the data and shuffling the data during training to attempt to make it work better at generalization. Um, and and that as a result that they do much better than HRM um, on the Sudoku extreme, um, and that the self-attention is better at the other tasks, um, but uh, but they're not uh, exactly certain as to why. Um, that with this, the self-attention, it they claim the accuracy is uh, significantly higher than HRM for the other results, uh, the non-Sudoku. Um, and that it should be a better model, a better architecture for uh, the same things that HRM might have done. But um, but as Ted pointed out from the drawbacks from the last meeting, um, it's we're not exactly sure that it would work well on other problems presented to it that aren't uh, things for which it's not been uh, trained so heavily, the small sample set that it's been trained so heavily on. Uh, so the claim is that without using the theoretical underpinnings of HRM, the biological model, that TRM uh, is simpler and faster and more efficient, but um, we're going to need more experimentation to actually validate the hypothesis. Um, okay, so as I say here, replacing the self-attention with MLP is extremely well on Sudoku, um, but that model, that architecture was worse on the other data sets. So it's the architecture is limited, and uh, we just don't know. It's going to have to be proven better, basically, is it? So I guess that's all, unless anyone has
Tom,
any.
Ted had made in an offline discussion or conversation he and I had that I didn't really pick up is, in that when they talk about it, even up in the beginning, they talk about being better than DeepSeek R1 and Gemini 2.5 um, and stuff like that. And I guess in my head, I just thought they were kind of equivalent but smaller. But this, Ted, you were saying these are not generative models that they're talking about with TRM, right? And they're not, they seem to be a very specific set of, like, I also thought the AGI, um, ARC AGI tests would be something that would be more language reasoning is kind of the areas that we'd explored before. But that doesn't seem to be the case. Is that right?
Yeah, so I think there's a couple things for me that are super important about the results. So one is I think that Sudoku and Maze are relatively easy problems, um, just as problems go. And then on top of that, when HRM or TRM were trained to solve those, they were trained just to solve that one thing, just Maze or just Sudoku. Okay,
Mhm.
so the three different things they solved were three separate trainings.
And would they
Okay,
have been separate? So this isn't like a language generative thing. So they would have been trained with a specific head for that test and a different head for that test. Is that how it
so
works?
in the end, I think the architecture was identical for all three trainings.
Okay.
Okay, I think what they did is they said, what's the largest size problem we have? For Sudoku, it's 9 by 9. For Maze, it was like 30 by 30 or whatever. And for ArcAGI, I think it was less than 30. So I think they just went with 30 by 30. Okay. But the other thing that's important to know is that they designed HRM and therefore TRM as BERT style fixed width encoder models. And so they are 30 by 30s, 900 cells. So they take inputs that are 900 cells, 900 tokens long. Okay. And then In parallel, all 900 of those are processed. And then for each iteration or whatever, that they go through all the layers and then you get outputs. So
And
if you were doing a breadth first search, right, hypothetically, you could say, of the 900 pixels, I know which one is to my left, which one is to my right, which one is above me, which one is below me. Right. It's going to be a little different for each position, but in training, you can basically just learn, right? And so then basically you can say if my current value is not yet visited and the one to the left, up, down, or right, if any of those four are visited, then I'm going to change, my value to
yeah,
visited.
yeah.
That would be a very straightforward way of doing breadth first search. So by virtue of implementing this as a not generative model, okay, if you say that the model is doing whatever, six things 50 times, whatever, the equivalent of 300, depth 300, okay, what you're really doing is all 900 positions in parallel, those 6 times 50 times. Okay. So if you were to just kind of write out all the flops, okay, and you were to try to implement this on CPU, what you would see is that it's basically saying for locations 1 through 300 each, do the layer 1 calculation. And then for locations 1 through 300 each, do the layer 2 calculation, layer 3, whatever, right? So it gets confusing with all the for loops. But so when you talk about this model having sort of that inner loop and that outer loop, and then you talk about having deep supervision, okay, within all of those loops, it's actually looping 300 over all the cells. Or for Sudoku, there's only 81, whatever, for whatever size the grid is. Okay. So in terms of like the number of flops, this is doing something kind of very different. And so what I would argue is that if you just wanted to do something like here's a checkerboard, I only have two values, 0 and 1, white and black, and I just want you to reverse the checkerboard. Okay. GPT-5 may stumble on that task, not because it can't understand it, but just because it has to do bookkeeping on 64 different things to just simply output an accurate reverse checkboard. You know what I'm saying? Even if conceptually it knows what it wants to do, it has so much bookkeeping to do to say, let me go back and look at the first cell. It was white, so I'm going to output black. What was the second cell? It was black. I'm going to output white. You know what I mean?
Yeah, I think I
So
did the is this I think this is the problem outlined in that recurrence incompleteness paper, in that since they can't manage state if they're walking through uh, a quote unquote computationally irreducible problem, when you have to compute n plus 1, n plus 2, you can't go from n to n plus 2 without actually walking across n plus 1. The yeah, the transformer architecture doesn't have a mechanism to track n through n plus 1
Yeah.
through n plus 2. So as such, it's always going to have to like try to guess what that is, for complex like state tracking stuff.
Yeah. So, like to use a human analogy more simplistically, if I had one of those Caesar substitution ciphers, in those cryptograms where you just say, like, replace each letter with some other letter, right? So A gets replaced with whatever, T, and B gets replaced with L or whatever, right? If I gave you a string that was 80 letters long and I said, encode this just by swapping these letters, you might make mistakes and it might take you a little while longer just kind of writing it out. But if instead I said, here's the 80 letters, and beneath each one, do the substitution, it might be a lot easier because you're just kind of doing it in a one-to-one correspondence instead of constantly looking back and trying to figure out where you were. Does that make sense? So that's one of the key things that I think is 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 not always talked about is that if you try and use GPT-5, it has to do this generative thing and it has to do all this bookkeeping just just to even refer back to what the problem was accurately.
So Ted, from your understanding, what's this experiment look like? Do I fit it in? I've got 30 by 30, so I've got 900 tokens, a sequence of 900 tokens representing the value of each cell in
Mhm.
the maze. And I've got these multiple layers, and then on the top is some sort of what 300 by or 30 by 30, 900 sequence of 900 cells that I will visit. Is that is that kind of
Well, so if you unroll all the for loops,
uh-huh.
okay, I know that the actual implementation uses for loops, but if you simplify things and just unroll them,
Yep.
okay, then this becomes like the equivalent of a whatever 200 layer model or whatever,
Right.
right?
Right.
So then you're just going to input 900 tokens, and after 200 layers, you're going to get 900 tokens. That's your predicted answer. That's all.
Yeah. Okay. And
Okay.
I also so looking through like the Arc AGI, I expected those again to be reasoning types of word problems, I guess. But they seem to be again patterns that look for this pattern. Here's one pattern and what the output was from that. Okay, I'll give you a new pattern. Tell me what you think the output should be. So it might be
Yeah.
rotate the squares, and down here you know you've got triangles and you should rotate the triangles type of thing. So again, it for me it was a little misleading to be comparing it against something like a Gemini, um, and in an AGI reasoning task. Um, I had a lot higher expectations than what it actually ended up being.
Yeah, so I mean, we could talk about ArcAGI as a separate thing. I think the the goal with ArcAGI is that they wanted to purposefully give you problems where they don't give you enough examples to fully define the problem.
Okay.
And you're supposed to use intelligence plus some kind of world bias to say this is the most reasonable explanation for what you did, even though you only gave me two examples.
Hmm. Hmm.
Okay. So there is this simplicity bias that they want you to apply, right? So if it just gives you like some random shapes that are different colors, and then in their answer, and all the shapes are enclosed, and then in their answer, they just fill in the enclosed stuff with blue pixels,
Hmm. Hmm.
regardless of what the color or shape of the original was. There's this, right? Like as humans, we would probably relate, say there's a simplicity bias that it's like just fill in the closed shapes with blue pixels.
Yeah.
And that's their intelligence test that without giving you any verbal instructions, without giving you enough information to truly understand the pattern, there may be 1,000 different patterns that technically are valid on just the mere two examples they gave you. But one of them we would say is intuitive, like fill in the shapes. Whereas if somebody had said, well, for every pixel that if you multiply the row and the height and you take it modulo 25 and subtract 2 and da da da, if it's odd, then fill it in blue, right?
Yeah.
And
Yeah.
that technique might work, but we wouldn't necessarily think that's a intuitive algorithm compared to fill in the
Yeah.
shapes.
Yeah. Yeah. Anyhow.
It's debatable whether or not that truly is a great way to measure things or whatever. But so they wanted to go beyond like memorization and whatever, and they wanted to purposefully not give you instructions, which is why it's visual and not text.
Yeah. Yeah.
But so going back to the original thing is unfortunately in ArcAGI, there are a few tasks that are quite simple. And so getting whatever percent they got on that, it's not clear how smart the model really was.
Hmm.
ArcAGI 2 is a lot harder, and that's why you see things are at like 5% correct.
Okay. All right. Anybody have anything else, or are we ready to wrap up that one? Okay, let's call it a wrap up. Thank you, Alfonso, for walking us through that. Um, and then Shreyas, are you ready then to present? I guess we'll kind of just roll into when we post it on YouTube, we'll provide a link for the midpoint and
Yeah,
do a
of course.
discussion. So, okay.
Of course.
Um, you'll let's see. Alfonso, do you want to stop share? Okay, great. And then I don't know how Ted's got it set up right now, but Shreyas, you need to ask if you're presumably going to be presenting something in share desktop. Yep.
Is it
Yeah, it looks
visible?
like it's coming. It's not there completely, but it's getting there. Yep.
Right, there we go.
Yeah, we can see it.
Yep. You're going to need to zoom in a bit for me at least, though. Yeah. Yeah. Great. Thanks.
Yeah. Uh, okay. Hello. My name is Shreyas. I'm currently an AI performance and infra intern at Enhansa. And today, the paper that I'm presenting is a quantitative study of locality in GPU caches for memory divergent workloads. So 30,000 foot view of this paper is essentially that at the time of this paper, there were numerous papers already published that looked into taking advantage of locality to optimize GPU performance, but none of them really went into the nitty gritty quantitative metrics and didn't produce any like solid quantitative studies that people could refer to make further optimizations. So primarily, this paper looks at cache optimization from the perspective of memory divergent workloads. So, I mean, the way that I'm going to go through this paper is pretty much just read and then stop at points where I think it's interesting, or stop at points where I think we should note some stuff. I'm gonna move it like this. Is this still visible for everybody, or is it? Um,
It's cutting out on the right. Oh no, actually, it's good. It's pretty good.
okay, is it? Uh, there we go. Is that good?
Yep. That's good.
Okay, sounds good. So start off, GPUs are capable of delivering peak performance in teraflops. However, peak performance is often difficult to achieve due to severe performance bottlenecks. Memory divergence is one such performance bottleneck that makes it harder to exploit locality, causes cache thrashing and high miss rate, therefore impeding GPU performance. And essentially, what this means is that there are certain applications known as irregular applications where generally when your GPU cache is processing a warp or a collection of 32 threads, each of those threads are accessing memory addresses that cannot be compressed into one 128 byte cache line. So they have to have multiple cache line calls from the DRAM and then move it into cache for use by the GPU, or but for use by the threads. Um, as data locality is crucial for performance, there have been several efforts to exploit data locality in GPUs. However, there is a lack of quantitative analysis of data locality, which could pave the way for optimizations. In this paper, we quantitatively study the data locality and its limits in GPUs at different granularities. The granularities that they go into are the warp level and CTA level. CTA, or thread block. CTA is the NVIDIA terminology for thread lock, but essentially what CTAs are they're a coordination of multiple warps that, that belong to one SM, or a streaming multiprocessor.
Shreyas,
Yeah.
can we define what does data locality mean? Is it um, the same layer or level of memory? Is it locality relative to an SM? Is it locality within some range of memory addresses?
Yeah. So in the paper, They generally focus on L1 and L2 cache. So L1 is specific to each SM, and within each SM, there's multiple CTAs. So over the course of the paper, what you'll see is that the paper not only delves into inter and intra-warp locality or reuse of cache lines, it also goes into warps within a CTA, and checks what the cache line reuse and spatial locality is within the warp and between warps that belong to the same CTA.
Okay.
So Roger, basically data locality here means that the data accessed by various threads are adjacent to each other, such that all the data can be fetched from one cache access. So let's imagine the memory subsystem is fetching the data into the cache, and if they are all belonging to the same contiguous, let's say, call it 256 byte blocks, then you have high data locality in those threads that implement that algorithm.
Okay. So that was one of my questions. So it's like 256 bytes is if you access L1, and that's how much you access at a time. That's kind of the bus um, memory bus width.
Right, right. So basically, that means the memory subsystem does not need to make multiple calls to replenish the cache.
Right.
Basically, that's basically what it means.
Yeah. Okay. Thank you.
Yeah, go ahead.
Sorry, if I could ask a basic question, and if it's going to get answered later, that's fine. But I would assume that we're kind of always trying to read large contiguous blocks. I mean, that's my understanding of the way we organize things. So, does this divergence, non-locality, get introduced because we have, um, let's say, a parameter and we're multiplying and we need to access it column wise, but we've arranged the data row wise, and therefore now we're kind of screwed and we don't have great big
That's exactly
contiguous
right.
blocks.
You got the
Yeah.
right question there. So they will go through. I don't want to steal your thunder there, Shreyas. You answer that one.
Yeah, so essentially, if we go down, they run like numerous benchmarks, and one of the benchmarks is histogram, and this number essentially here is the coalescing efficiency, and what it does simply just like measure the memory divergence of a certain benchmark or kernel. And the lower the number, the more memory divergent it is. And I was going through this yesterday with my mentor Srini, and we were talking about why histogram would have this level of memory divergence. And we couldn't find the exact code for the kernel that they were using, but our assumption is it's like the atomic operations, and generally what it is that when you're accessing based on parameters, it'll access addresses that are very widely spaced because of some lack of optimization within histogram, because histogram can be optimized to not be a memory divergent thing. But if you see over here, they purposefully used very memory divergent. So yeah, from each benchmark, we select a single kernel launch with the highest memory divergence, and when benchmark has multiple kernels, we only include kernels that have memory divergence. I don't know if that answers your question.
Yeah. So one of the things, the dream here is to be able to characterize. You go look at an application and say, "Hey, is this parallelizable? How parallelizable is it? Can you develop a metric that says you can achieve a high degree of parallelism in this particular code?" So everybody wants to do that when they migrate from CPU to GPU, and that's the dream, right? So this is one of the things. There's synchronization points and there is data localization. So those two are key performance killers, and you want to optimize for both. So as Shreyas was saying, the histogram, it's the problem is more of synchronization. It's not so much as memory. So think of the histogram is computing 100 numbers, and let's say they vary, for simplicity, they vary from 1 to 100 only, and you are classifying them into bins of 10. So a simple algorithm could be, hey, go access a memory, you find the value, just integer divide by 10, and then go use that as an index into an array and increment the counter. So that's a simple histogram algorithm, right? But what happens is this is not parallelizable. It's very serial. So in other words, if you run, let's say, 32 threads of warp to do this thing, you all the 32 threads cannot be running parallelly because they could be accessing exact same data and incrementing it. So it has to be serialized. Bobby, you have a question?
Yeah, so we know the warp size is 32, right? So we should be able to align each thread to access that cache line, right? So you said the cache line is like a 128 or something. So
Right.
that specific warp thread could be able to process that 128 elements, right? That way there will be no overlap.
It absolutely right. You are absolutely right. So it depends on how you implement the algorithm itself, right? There are multiple ways of doing, say, histogram, right? So if you do it in a certain way, you could actually get more memory divergence and more synchronization issues
Yeah.
that
So
damage.
the point I'm trying to make is that this is a solved problem for many decades. So if somebody wrote a incorrect code, then what's the point in analyzing it, right? I'm not understanding it properly.
Not incorrect, I won't say incorrect code, it's unoptimized code for, I mean, in optimized code, there is a spectrum between 0 and 1. So it will be highly optimized or not at all optimized. And of course, there is whole range in between, right? So it depends on how you design your algorithm and implement it for that particular thing. So yes, to your point, it is you have to actually deeply look at the code. You have to do a deep inspection to figure out whether it will
Yeah,
suffer that performance.
yeah. To add your point, so that is parallel programming 101. So you're trying to have optimize all the resources with maximum utilization. So obviously you're going to take the data and partition it exactly that well aligns with all those resources, right? Then you
That's right.
should be able to go with full speed. So if you're going to have overlaps, then you're not going to fully utilize the resources that are available. So yeah,
Exactly right.
yeah. Thank you.
Okay. Um, but yeah, so the primary findings that they find in the study is that um, based on or compared to previous studies, they find that there's a lot more interwarp locality, and what that essentially means is that within an SM, there's a lot of reuse or cache line use uh, between warps or within the same warp by different threads, or sorry, between different warps within an SM, uh, and so
So Shreyas, maybe it's good to define these terminologies, SM, warp, CTA, all that stuff.
yeah, of course. In fact, I think it'll be beneficial to go through section 2, where it goes through the typical like memory hierarchy of GPUs. At least at this time, they stop at. I know we have more modern architectures like Hopper, Blackwell, and Ada Lovelace, but this paper is uh, somewhat old in the sense that it only has up until Ampere architecture. But that being said, memory hierarchy in GPUs can be divided into multiple streaming multiprocessors. That's what SMs are, and each SM. Oh, sorry. Uh, I just went to a. There we go. Yeah, so each SM is kind of analogous to cores and CPUs, but they have a much simpler structure, and the advantage is that they can execute significantly more threads in parallel. Each SM has a register, which contains like 32-bit slots that are private per thread and allocated by the compiler. They also have shared memory, which is shared between warps in a CTA and can be controlled by the programmer in terms of allocation. There's Each SM also has L1 or L1 cache, which is hardware managed and is available to all CTAs in an SM. And when I mention CTA, what I mean is that CTAs um, are a kind of unit of computation, if you will, that contains multiple warps. So one CTA can have, like, just as like a rough number, it can have like 8 warps, and each of these warps are a collection of 32 threads that are executing the same function in parallel. And so uh, generally, if you see that down here around here, let me find it. So over here, the main purpose of this paper is that GPU memory hierarchy. Um, it's hard to exploit locality because of the large number of threads and the significantly smaller caches. In CPUs, we'll see that each core has around like 16 threads, and like for example down here it says the Intel Core i9 9900K CPU has um, like 256 kilobytes, 2 megabytes, and 16 megabytes of L1, L2, and L3 data caches, respectively. And this divided among 16 threads comes out to like 16 kilobytes, 128 kilobytes, and 1 megabyte. But if we take that same math and apply it to any of the modern architectures as shown here in table 1, we'll see that per SM or GPU, you have um, for the entire GPU, you'll have around like thousands and thousands of threads. While per each SM, you'll have around like a couple thousand threads. And when you divide L1 amongst the SM, you'll see that if we were to take this number, which is for each SM, and each SM has its own L1 cache, we get that there's only about 32 bytes of cache per thread. So that's why it's much harder to exploit locality, because you have data coming into the cache and moving out of the cache in very rapid succession, such that before reuse can actually happen, the cache, like the cache line, is evicted. And that's something that is actually investigated later in the paper in the results section. But so the main purpose of this paper is to kind of understand quantitatively how um, how we can exploit locality, and it uses a simulator essentially rather than actual GPUs, because in the simulator they're allowed to simulate unbounded amounts of cache. So normally at this time you have GPUs with around like a couple kilobytes of L1 cache. In the paper, they use 16 kilobytes of L1 cache. And then in order to understand the limit or the maximum amount of locality, or like exploitation of locality, whether it comes to reuse or whether it comes to spatial utilization, they rerun the simulation for each of these benchmarks with an infinite amount of cache. So it's kind of to see what the upper limits are for optimization and see where we might be missing out on optimizations when it comes to GPU architecture.
Roger has a
So I'm sorry.
Roger has a question.
Oh
Yeah,
yeah.
yeah. I was wondering. I hadn't seen those tables, the one that you had that showed the number of bytes per thread, um, and kind of surprised at how small those caches were. Do you know? Is it typically do you typically use all the threads and you actually end up with caches that small per thread?
Yeah, so uh, I mean, what we realize is that there's a good chance. So in the paper focuses on memory divergent applications or GPUs in the face of memory divergence. So in that case, each thread is accessing vastly different data from one another, and that's leading to repeated memory transactions. For which, yes, in that case, each thread only is able to exploit this amount of cache. But ideally, what you would want is applications like, for example, like previously said, um, applications that are optimized in a manner such that um, there's reuse between threads within a warp, between threads across a warp. The paper actually shows that with infinite cache, you will see a pretty significant amount of spatial locality uh, utilization of a cache line intra CTA and inter warp, meaning that within the same CTA across different warps, you'll see that the threads across all of these different warps end up using the same data or the same cache line that's been brought into L1 cache. So ideally, that's the situation you'd want, and that's what um, the GPU attempts to do. The GPU attempts to take all of the memory requests. So over here, you'll see that there's this coalescing efficiency value, and what it essentially represents is that it's trying to show that for a certain warp, there's 32 instructions, one for each thread. And what the GPU ideally tries to do is take all of these threads and find a way that it can issue a single memory transaction that brings in all of the data necessary for all of these threads to run parallel. But there is a limitation sometimes with certain applications where each thread has control or memory divergence in the sense that it needs vastly different amounts of data or it's going through an entirely different line of logic where you will have in this paper it's defined like a single memory transaction is defined as like the number of times a cache line is fetched from CPU DRAM. So in that case, what they do in order to get this percentage value is that they say, okay, we have 32 instructions. Generally, the GMI is at 32, and then if you can coalesce all of these instructions and take uh, like coalesce them into one transaction where all of the data for all of these 32 threads can be brought from one cache line fetch from the DRAM, then that's the highest efficiency. So you can see here, it would be 32 divided by 1, and then to normalize it into a percentage, they divided by 32 again. So if we were to take a perfectly coalesced application, we would have 32 instructions, but only one memory transaction. And then we divide that by 32 to get 100% coalescing efficiency. On the other end of the spectrum, worst case scenario would be that for 32 instructions, you need 32 different like memory transactions or cache line fetches from the DRAM. And that would be 32 divided by 32 would become 1. And then you would have 1 divided by 32. So it would be about a 3% coalescing efficiency. Um, so yeah, so there are applications in which, the thread size the L1 cache available per thread is that small, but that's ideally not the case. But that's what the paper studies. The paper aims to study applications in which that's the case.
So Shreyas, their simulator is measuring the coalescing efficiency. They also make a remark that Insight, which is a tool done by NVIDIA,
Yeah, right over
that
here.
actually runs on the GPU, and it also has one of those benchmarks, right? So it
Yeah,
measures.
so yeah, so it mentions that coalescing efficiency metric is also reported by NVIDIA's profiler, which is Nsight. But Nsight defines it a little bit differently from what's defined in this paper. So in this paper, it defines a memory transaction as the number of times a cache line is fetched from a GPU DRAM. But in Nsight, it's generally defined as the number of times a cache line needs to be fetched into L1, whether that's from L2 or DRAM or any other, intermediary.
So any level of cache
Yeah,
fetch.
pretty much.
So if this is you cover this later on that just postpone it, but what this allocation of where the data should be, how it should be allocated in memory, what currently takes care of that? Is that it's manually done when you're writing up? Is it something in the CUDA compiler? If I'm programming in Triton, where does this take place? Who worries
Yeah,
about that?
that's actually a great question. So, um, the very first sentence of this section actually goes into exactly that, right? Where it says the first general purpose GPU architecture, which is the Tesla architecture, had programmer managed caches, but nowadays they've transitioned into hardware managed caches. And what they've seen is that this, the hardware managed cache plays the important role in the higher performance of these new gen GPUs. But we can also see that sometimes this can be kind of like an Achilles heel, where where oh sorry, I'm blanking out, where the program, or sorry, the hardware managed cache could actually be a pitfall where it would. I'm trying to find the line. There's a line here that goes into how hardware managed cache could also be negative.
So let me try it differently. So Roger asked, I think, is a different question, which
Oh,
is
sorry.
really how do you partition the algorithms, the threads, the warps, and so on, so that the memory they access is arranged contiguously?
It's
That's
also, yeah,
the
the question was also who is
right.
doing
Who's
the assignment? Who's creating the memory layout?
It's really the compiler, the CUDA.
Yeah,
That CUDA that does that? Okay.
Yes. See, the cache is managed when they talk about hardware managed cache. It's really the memory subsystem of the processor itself that fetches, how the cache is replenished and so on. That's a different issue. The issue you are talking about, Roger, was, if I understand it right, is if let's say you are writing an algorithm like a histogram, right? And I write a program. Now, who allocates the memory the variables that I declare, where to put it in the memory? So that's
Right.
really the parallelizing compiler um, that knows about the GPU architecture, and it has to arrange things contiguously, presumably by looking at your logic and how it is accessing memory.
Right. Okay.
yeah. I think the only part of uh, of the memory hierarchy that you can design or you can control and dictate how it allocates is the shared memory, right over here. I don't know if I can highlight it, but it's this little green box that's individual for each SM. And that the shared memory is shared between warps within a single CTA, or it's shared with it's shared intra CTA. And that is the only piece of the memory hierarchy that you will be able to define, or you will be able to control as a programmer. But the rest is generally dictated by the compiler and the hardware itself.
Okay. What?
So one of the things here is that, see, there are 32 threads in a warp, and apparently all 32 threads in a warp has to execute exact same instruction. So
Mhm.
they're all parallel, right? So they are executing the same instruction, but presumably using different data. The CTA is a collection of these warps, which is cooperative thread array. Is a collection of these warps, and all these there are multiple CTAs that are co-located in a SM, or symmetric multiprocessor. So presumably you will design those CTAs to use the shared memory that is local to the symmetric multiprocessor. And you will also arrange the memory that they use in a way that it fits into the cache lines, L1 and L2 cache lines.
Gotcha. Gotcha. Okay. The one other question I had, sure, yes, as you were going through, you described it as the registers being allocated. I just wanted to check my mental model here. So I'm thinking of this as like a multiprocessor, and you've got kind of each of these threads has the same set of registers. Is that right? Or is it actually
No,
more of a pool of registers?
so the registers, they actually are private per thread
Okay,
within
okay. And
GPUs.
every thread has the same number of registers.
Yes,
Yeah, okay,
yes,
okay. That's matches what I thought then. Okay, thank you.
yeah. Um, yeah. So where was I? So I mean, I guess if the primary problem is, and by the way, I found the line where it said that exploiting locality is hard due to a large number of active threads and smaller caches. In fact, some works reported negative performance with hardware managed caches. So, I mean, generally in modern GPU architectures, you will find only hardware managed caches. Um, and the negative performance can be attributed to the findings found later in the paper, where we see that at times the hardware defined um, the scheduler, it doesn't optimize for locality and reuse. So we'll get into that later. Um, but yeah, so this entire section kind of just goes into the difference between CPU, GPU, and how GPUs have much smaller amounts of cache per thread. And then this goes into how you have streaming multiprocessors, which are the SMs. You have a thread block, which is divided into warps, and which we have you have multiple thread blocks within an SM. A warp consists of 32 threads. They all execute the same instruction, and a thread block can be scheduled on any SM. So this is actually a pretty important line. So yeah, so let me just make sure. As thread blocks can be scheduled on any SM, it is very hard to exploit inter-thread block locality at L1 caches, because L1 cache is private to an SM. So if we see up here, we can see that each of these SMs, they have their own L1 cache. But when a GPU encounters, say, a set of 8 thread blocks, or 6 thread blocks, and it has 3 SMs, right? It can assign each of these thread blocks, or CTAs, to an SM randomly. So two CTAs might have a lot of overlap in terms of the cache lines that they need, but due to the random assignment between these streamlined multiprocessor or streaming multiprocessors, it sometimes is hard to exploit inter-thread block locality. And to continue on, So this is where L2 cache comes in.
Hey, Shreyas,
L yeah.
so just to parrot back what you just said for my understanding,
Mhm.
um, so if I write my own custom CUDA kernel, I cannot choose streaming multiprocessors. That's not
Okay,
one of
so
the
I
options
might be
available.
entirely wrong here, but from my understanding, no. So this is something I have to look into. I honestly, what I would say, I don't know. Like, do not take my
Yeah.
answer as
Okay.
like, yeah,
I
I
Yeah.
don't know exactly.
But so
I
parroting back what you just said about like, there could be high reuse. I mean, imagine that you just had a set of data that was enough work, you know, but you just had whatever, two sets of things and you wanted to add A and B and you wanted to multiply A and B, and you wanted to divide A and B, and you're just using A and B over and over and over and over and over again. It might be faster to just have it all live on one streaming multiprocessor and have it all pull A and B off the cache over and over again.
Correct.
But if you can't choose that, then it might actually assign these 20 operations to 20 different, and then you're just going to load A and B 20 times when you really kind of didn't need to.
Exactly.
So I just did a quick Google search. It just apparently you cannot pin a thread block to an SM. That was the feature in CPUs, in multi-core CPUs. You could actually pin a particular thread to a particular multi-core processor, whereas in the GPUs, you cannot do that apparently. So the scheduler, GPU scheduler, does that by itself. Maybe in future they will bring up that feature, Ted, that you talked about.
Yeah.
Yeah, and
The
it would also
reason
be hard because you could be running on different GPUs that have different numbers of streaming multiprocessors and all these things. And so, uh, probably most of the time, you do want it to figure it out for you. But
Yeah.
to the
Yeah,
author's point,
sometimes
it
you
makes it
want the
hard.
flexibility of pinning it too, right? I mean, it's you don't need to pin it. You can leave it to the scheduler. So, Bobby, you have a question?
Yeah, one point is that the cache eviction happens only if there is a write, right? Like for example, if the read is more write is conflicting with the read, then only it will be get evicted. So if it is all reads, then there won't be a conflict, right?
No,
so
not true.
yeah, to answer that question, GPUs have a kind of weird sort of write and allocation protocol in the sense that any local access and local write will be like a write and allocate. And what it will do, it'll probably stay within L1, L2 after writing to DRAM. But if you're looking at more global accesses, um, like for example, um, like
So
shared
sure.
memory. By the way, just for clarification, shared memory is not global memory, but global memory is essentially shared by threads, warps, CTAs, etc. And it's usually stored off chip in the DRAM and allocated with the CUDA malloc function, or it's passed as kernel parameters. And generally, it's found in the L1, L2 cache hierarchy. But what the GPU does is it kind of decides, okay, this is something that isn't going to be used because local access is like data that's private to each thread. So the GPU kind of knows that this thread is most likely going to be reusing this data down the line.
Okay. Okay,
And
I get you what you're saying. So my question is much more simpler than that. So you have two read-only buffers, and you are taking the data from those two read-only buffers, and you are adding them and writing to the another buffer that is write-only. So there is no conflict in when doing the operations on these two read-only buffers, right? So you read the data and you keep on adding them and putting it to the another buffer. So there won't be any conflict here, right? So how much cache line that you pull in, there is no conflict to evict from the cache, right?
No, actually,
Yeah.
Bobby, there is. Let me give you a scenario here. So let's say you are reading an array continuously, okay? And that let's, for simplicity's sake, let's say your cache fetches, the cache line width is only 16 bytes.
Mm-hmm.
Okay? And the array is whatever, 1024 bytes long, right?
Mm.
So each time you're going to say, hey, access zero member, it's going to fetch the entire 16
Yes.
to into the cache, right?
Mm-hmm.
So you're going to read 16. Now, when time comes to read the 17th byte, the cache needs to be evicted, and then the next block has to be brought in.
No, no, no. I understand because it is a spatial locality. So you consume the data that you got, and then you want to fetch the new data, and there is
Yes,
no space in the cache. Then at that point you evict. The
exactly.
point is that you won't be evicting while you're using it, right?
That's right.
Yeah. That's why. So if there is a read only, so there won't be any eviction if there is no conflict of rights.
That's
And
right.
the other point that Ted was saying that if you have a very big and um, operations on two big buffers, so here instead of you consuming only one streaming multiprocessor, for example, if you have a 20,000 bytes that you want to add from two different arrays, 20,000 bytes in two different arrays, and you have 20,000 processors, you are going to do one operation. You pull in the 20,000 and do one at a time, and then that's it. So that way you're pushing the entire data at once as a single shot.
That is
Yep.
true.
Right,
If you
right. I was saying more you have this let's say you have a handful of arrays, A, B, C, and D, and you want to calculate A plus B, and then you want to calculate B plus C, and then you want to
Mhm.
calculate C plus D, but then you want to calculate A plus C and A plus D and B plus, right? You're reusing these things, but you're not reusing them soon enough. So then likely what's going to happen is you're going to get zero cache hits because by the time you try to do A plus C, it's already done whatever D plus E and it's no longer there or
Yeah, yeah.
whatever.
You're doing one operation at a time. So yeah,
Right.
but it is
Um,
in parallel, like in a full force. Yeah.
yeah. So what I've seen is that if you know this is the pattern, then you can explicitly put A, B, C, D, and E in shared memory, because then you know it will be there until you overwrite it with something else. And that's better than having a cache miss, but it's not as good as having an L1 cache hit.
Yeah. Sure. Thank you.
Shreyas, can I ask one quick question with respect to
Yeah,
kind of
of
GPU
course. Go for it.
background? So you covered these topics, threads, warps, SMs, etc. Um, are these terms all unique to NVIDIA GPUs, is it something where different GPUs have different types of architecture?
Okay, so yes and no. So this paper primarily looks at NVIDIA GPUs, but they explicitly state that most of the findings of this paper can be applied to AMD GPUs and other architectures as well. That being said, CTA, like the terminology CTA, is NVIDIA specific. Generally, if you want to refer to them across all GPUs, you would want to use the term thread block. That being said, SMs, warps, thread blocks, these are all pretty common terminology across all GPUs. In
Okay.
fact, I think they mentioned this earlier. I'm gonna try to find the line. Okay, yeah. So our study focuses on NVIDIA architectures, which dominate the discrete GPU market. However, we believe the findings mostly apply to AMD architectures as well, because both of them have a similar cache hierarchy. That being said, this paper is 2022. I don't know how the hierarchies may have changed. I don't know if there's going to be that big of a change uh, from 2022 to now. It's very possible, but I don't think there is.
Got it. Thank you.
Of course. Any other questions?
So how long do we have, Roger? We are already approaching 8
Yeah,
o'clock.
yeah, we're gonna we try to cut off at 8 o'clock, and we kind of squeezed it here. So Unfortunately, this week, I think next week is Thanksgiving, right? So we'll have to skip next week. But if you're okay with it, depending on what your schedule is, et cetera, we can just continue on in the next virtual meeting, which is 2 weeks from now.
Yeah, of course. I do hope that I'm presenting this in an interesting enough manner. So
Oh yeah,
this is
no,
my first time
definitely.
presenting a paper.
And if you want to pick what you think is a good break point here, somewhere in the next, 10, 15 minutes.
Yeah, yeah, of course. I think I can get through pretty quickly, like section two, section three, and
Okay.
then we can like do a deep dive on the results next time because
Okay.
I think this is the meat of the paper, the results section. But a lot of it is just like a bunch of jibber jabber, and you could really just go in and kind of look at the diagrams, and I could summarize this all into like one session, one session.
Okay.
Does that sound okay?
Yeah, great plan.
Okay, of course. So yeah, so I mean, in this paper, typical cache line is 128 bytes, and they mentioned that in previous architectures, they didn't have sectored caches or cache lines, and what this essentially means is that later on, starting from the Kepler architecture, uh, the cache line can be subdivided into these units called sectors, and generally it's divided into four sectors. So if you have a 128 byte cache line, you will have 32 byte sectors. Um, and what this allows you to do is rather than overfetching and fetching the entire cache line, you can only fetch the sectors that you need or that you know that you will need for whatever whatever function your threads are doing. This also does come back to kind of uh, bite you in like the behind, because if you see like later on you'll see that having that kind of prevents reuse in L2 cache. For example, it's like a pretty astronomical jump in L2 cache, which is shared, where you'll see that over the course of the entire program's execution, if you have infinite L2 cache, you'll see that there's a lot of reuse and there's a lot of spatial locality where it would just benefit from taking the entire cache line and bringing it in rather than bringing in as sectored uh, or bringing in as sectors. So there's a common misconception that sectors are just kind of cache lines split into smaller cache lines, but the assumption is false because the four sectors that act as subblocks, while they have the same tag bits of their memory address, the differentiation of the sectors is stored in the um, address of the cache line after the tag bits. So normally we'll see that in cache only the tag bits are stored. So when you call in a cache line or when you're trying to call in a sector, you'll be calling in using those tag bits. But then if you want to define a certain sector, you can go further and define the parts of the memory address, including I think there's sector and also byte. So you can define exactly which sector you want and which byte you want in that sector using memory addresses. But you might another question that comes up is that you could just make cache lines smaller size and then you know use those, but the primary limitation that comes with that is that the amount of tag bits that need to be stored in the cache goes up linearly with the amount of cache lines that we have. So it's purely like a hardware design limitation in the sense that the more tag storage that you need, the more space on the actual chip that you're going to take up, that could be used for cache instead. So that's why sectors aren't smaller cache lines. They can only be kind of viewed as subblocks of cache lines. That being said, Going further, as a thread block, also known as CTA warp, can affect data locality. We classify and study locality at warp and thread lock granularities. So intra warp, inter warp. So intra would be within the same warp or CTA, and inter would be between two different warps or two different CTAs, and they pretty much study both reuse and especially they study spatial locality and hit and miss in the context of inter and inter warp and then inter and intra CTA. So as I previously mentioned, in the study, they used a simulator for simulating the different benchmarks and trying to get the quantitative data. The reason that they didn't use actual GPUs is that at the time it was incredibly hard to get all of the quantitative data necessary for the study. But the primary reason is that the simulator allows for them to conduct limit studies and hypothetical scenarios. For example, they can quantify maximum cache line reuse that's possible across kernels by simulating a GPU with infinite L1 cache rather than just a realistic 16 kilobyte L1 cache. And as we go down, we have the benchmarks. So table 4 shows the benchmarks used for evaluation, and each of these are kind of just different CUDA kernels, histogram, data analytics, yada, yada, yada. The CE defines how memory divergent this specific benchmark is, and you will see that reflected in the data. For example, the histogram is extremely memory divergent to the point where there's no L1 cache reuse within a 16 KB cache. But we'll get to that later. That comes down the line, and I'll explain that in detail. So yeah, so yeah, go ahead.
Sorry, super quick question. These tasks, when I see like histogram and I don't know, k-means clustering, like I I think of these as being fairly high level operations. I wasn't aware that these were sort of low level GPU operations.
Um, that I couldn't find so each of these are like there's two different papers that they use that define all of these different benchmarks. I'm not too sure on so they said that they're using the popular Rodinia benchmark suite. I'm not familiar with exactly what that is, and then CUDA SDK. Um, I'm assuming that they're selecting single kernel launches because they mentioned that they select the launches with the highest memory divergence. I'm not too sure. I assume that it's low level from what's being said in the paper, but I don't think I have experience enough to definitively tell you that these are low level operations.
So it's
Okay.
not low level. I think they are actually what are classified as CUDA kernels. So those are like CUDA library calls, if you will. I guess they are not primitive, but then they are aggregated enough that NVIDIA has implemented that using their own
Okay.
algorithm to do a certain thing.
Okay, cool. Yeah. I guess I hadn't really thought about it, but I now that I think about it, sure, there's times when um in the middle of some, you know, deep learning algorithm, I'll see they'll just do some small histogram on the distribution of something and then do some sort of
Yeah, there are things like binary tree search. If you go to that table right there, so there is a graph search, B plus tree, graph analytics, data
yeah.
mining. I don't know what it does. SS1, it's the BFS. That's I would assume it's best breadth.
Breadth first search.
Yeah. Okay. Yeah, because I tend to think just matrix multiply, matrix multiply, matrix multiply. But
Yeah, yeah.
there are other things people do on GPUs.
Yep. Yep. Um, but yeah, so they this just kind of goes through what the CE is. I think I went over previously where I mentioned that for a single warp, how they define it is that they take the 32 instructions that they have from the 32 different threads within the warp, and they see how many times there's memory transactions or pretty much calls for data to move from DRAM into the cache. And that's how they kind of define uh, CE. And then they normalize it by dividing it by 32 again to get a percentage value. Um, Going down, I want to see what else I have highlighted. I think that pretty much covers most of what I wanted to say. But I mean, one more thing is here you can see that they mention what their config was for their simulator. They actually have a GitHub. So if you go to if you go to this reference, you'll see that this links you to a GitHub, but this GitHub has since been updated. Um, I don't know if you would be able to find the version that was initially used in the paper, or maybe you could use the new version. I feel like you could. But if you were to want to run the experiment on your own or uh, on your computer and try to see what you get, um, you could go ahead and look at that repository. And this is the config for their simulator that we used. I think that's a good stopping point because if I get into results, I feel like I'll cut
Yeah.
off.
I think that's good.
Yeah.
We'll probably need a quick recap when we start, whatever day that is, 2 weeks from now. Yeah, it's a good, great point.
Okay, sounds good. Thank you guys so much for coming and listening to me yap about this.
We're
Thank you.
really
But
good one.
yeah, I hope that was informative, and I'll try to look into some of the questions that came up this time and see if I can get some clarifications for next time. Maybe I can start off with that.
Yeah, I'm curious about this question that Ted raised about these tasks,
Yeah.
and what represents a CUDA kernel and why I would do a histogram on a GPU,
hmm Yeah,
etc.
I'll take a look into that.
Yeah. All
Yeah,
right.
thanks. This is a cool topic.
Thank you so much, guys.
All right, JS.
All
And
right.
then Alfonso, thank you for wrapping up the last TRM paper. And I guess everybody have a nice holiday next week. So again, officially, I'll update the meetup, but we'll not be having the meeting next week.
Okay.
Okay.
Thanks, everyone. Good night and happy
Thank you
Thanksgiving.
so much.
Good Thanksgiving.
Yep. Happy Thanksgiving.
See ya.
Bye, guys.
Hey, Roger, just so you know, in 2 weeks, I'm going to be